Hello, and welcome back to Silent Cosmos for Sleep. Tonight, we're going to ask one of the oldest questions a human mind can hold up to the light and turn slowly. Is there a center of the universe? It sounds simple at first. Almost everything we know has a middle. A town has a square. A table has a center where you might rest something warm. A room has a place where the distances to the walls roughly balance out. We grow up surrounded by things with edges and shapes and middles, so it feels only natural to imagine the universe, being the grandest thing of all, must have one too. Surely, somewhere beyond the clouds of stars and rivers of galaxies, there is a special place, a cosmic downtown, a location where all directions begin, where space itself quietly nods and says, "Yes, this is the spot." And yet, the universe has a long and consistent history of disappointing our most comfortable assumptions. Before we go further, take a moment. Notice where you are right now, whether it's late evening or somewhere between wakefulness and sleep. Whether the room is quiet or there's soft rain nearby. You're somewhere real, and that's enough. Settle in. Let your shoulders fall. Let the day loosen its grip a little. There's no rush where we're going, because the destination, it turns out, may not exist in quite the way we expect. And that, as we'll discover, is one of the most interesting things about it. Why we want a middle. Approximately 10 minutes. Long before anyone had written down the word galaxy, there was a person standing outside in the dark, looking up, trying to make sense of where they were. No equations, no instruments, no glowing app that could name a star with a swipe. What they had was a human brain, and the human brain has always been extraordinarily good at one particular thing: searching for structure. We don't enjoy chaos for long. When faced with scattered information, the mind begins arranging it. We sort sounds into patterns, shapes into categories, events into stories. And one of the oldest and most reliable arrangements the brain reaches for is a center. A center feels stable. It implies order. If you know where the middle is, you know where everything else belongs. Think of how often daily life depends on this. We build towns around wells and squares and crossroads. We organize rooms around a fireplace or a window. Families, without consciously intending it, often orbit around one calm person who always knows where things are. Even conversations tend to drift toward one topic that becomes the center of attention. The mind reaches for anchors because drifting indefinitely is tiring. Now place an early human beneath the night sky. The ground feels completely still. The sun rises on one side, crosses slowly overhead, sets on the other. The stars wheel around a fixed point every night, regular as breathing. If the heavens appear to circle you every single night, without exception, why wouldn't you conclude you're standing in the middle? That wasn't foolishness. That was a sensible first model built from direct experience. And there was good psychological logic alongside the observational logic. Human life happened on Earth. Crops grew here. Rivers ran here. Birth, love, illness, grief, all of it unfolded on this particular ground. Why would the meaningful stage of existence not also be the center of the grand design? For ancient Babylonians, Egyptians, Greeks, Chinese scholars, Mesoamerican astronomers, and many others, the sky wasn't empty background. It was structured, active, and deeply connected to earthly life. Celestial motions guided planting calendars, navigation, and political ceremony. The heavens mattered practically. If the flooding of a river followed seasonal stars, if navigation depended on constellations, if kings linked their authority to cosmic order, then watching the sky carefully was serious business. And the sky rewarded that attention. Babylonian astronomers tracked planetary motions across centuries. Egyptian builders aligned monuments with celestial directions. These weren't casual observers leaning on fences. They were dedicated scholars, working within the best frameworks available. And nearly all of those frameworks began with a stationary Earth. The most influential framework came from Greek astronomy, especially through Aristotle and later through Claudius Ptolemy. In Ptolemy's system, Earth sat unmoving at the center, surrounded by nested spheres carrying the moon, the sun, the planets, and finally the fixed stars. It was elegant, it was orderly. Circular motion was considered perfect, and the heavens were perfect, so celestial bodies moved in circles. When planets behaved strangely, drifting forward, then appearing to move backward, then forward again, Ptolemy's system explained this through clever geometry, circles upon circles, smaller wheels riding on larger wheels. To modern ears, that may sound clumsy, but the system worked. It predicted planetary positions with real accuracy for centuries. That's worth acknowledging. A model can be wrong in its ultimate structure while remaining genuinely useful in prediction. Ptolemy's astronomy was not nonsense. It was a successful approximation within its limits, and we still do this today. Newtonian physics isn't the final word on reality, but it remains excellent for bridges and spacecraft. The central Earth also resonated spiritually. Many traditions imagined vertical layers, heavens above, underworld below, human world in between. Sacred mountains and temples represented links between these realms. If Earth was the meeting place of cosmic zones, then centrality felt like more than geometry. It felt like significance. And here's the subtle thing worth sitting with. Even now, the ground feels completely still. The Earth spins at roughly 1,670 kilometers per hour at the equator and orbits the Sun at about 107,000 kilometers per hour. We feel none of it directly. Everyday experience still whispers that we are stationary. The universe regularly asks us to distrust first impressions, but first impressions are emotionally powerful. Being central feels reassuring. It reduces uncertainty. It says, your place here is not random. So when people began to question geocentrism, they were asking something much more than a technical question about planetary orbits. They were asking humanity to reconsider its location in the scheme of things. That was no small request, and still greater requests were coming. Copernicus and the moving Earth. There are moments in history when the world changes loudly. Empires fall, machines roar to life, oceans are crossed for the first time. Everyone notices. Then there are moments when the world changes quietly. A person sits at a desk, papers gather, a lamp burns low, numbers are checked, diagrams are redrawn. No trumpet sounds. Nicholas Copernicus belongs to the second kind of moment. Born in 1473 in what is now Poland, Copernicus was not a rebellious iconoclast charging at tradition for sport. He was educated, careful, mathematically skilled, and deeply familiar with the astronomy he would eventually challenge. He studied canon law, medicine, mathematics, and astronomy. He served in church administration. By most measures, he was a serious and respectable person, which makes what he did quietly remarkable. What troubled him wasn't that the old model was ancient. It was that it lacked harmony. The geocentric system had accumulated centuries of adjustments, circles upon circles, offsets, corrections layered on earlier corrections. The model still functioned, but it had become like a clock repaired so many times with improvised parts that it still told time, yet no one felt proud opening the case. Copernicus suspected the confusion came not from the heavens themselves, but from where observers had placed themselves within them. That suspicion was radical. Sometimes the hardest thing to question is not a technical detail, but the viewpoint from which all details are arranged. His proposal was elegant in its simplicity. Place the Sun near the center. Let Earth become one planet among several orbiting it. And many of the most puzzling planetary behaviors begin to resolve on their own. Those strange backward loops that required so much geometric machinery, they become a simple perspective effect. When Earth overtakes a slower outer planet in its orbit, that planet appears for a time to slide backward against the background stars. The same way a slower car seems to drift backward when you pass it on a road. No actual reversal, no elaborate correction required, just a shift in viewpoint. Mercury and Venus, which in the old system had always behaved differently from the outer planets, staying suspiciously close to the Sun in the sky, now had a natural explanation. Their orbits lie inside Earth's orbit. Of course they stay near the Sun. They can't wander far from it. Pattern after pattern simplified when the frame of reference changed. This is one of science's most satisfying moments, when a mystery dissolves not because new information was added, but because the wrong assumption was removed. Copernicus spent decades developing and refining these ideas. He was in no hurry to publish, and with reason. Established systems don't surrender gracefully. New ideas can invite criticism, misunderstanding, or worse. Especially when they challenge beliefs connected not only to astronomy, but to broader views of humanity's place in creation. His major work, De Revolutionibus Orbium Coelestium, was published in 1543, the year of his death. It did not immediately overturn the world. Contrary to the dramatic version of events, people didn't wake the next morning gasping into the streets. Intellectual change is slower than sunrise. Many scholars treated the heliocentric model as a useful calculating tool rather than a literal description of reality. Others admired the mathematics while doubting the physics. Their doubts were not unreasonable. If Earth truly moves, why don't we feel it? Why do objects dropped from high towers fall straight down rather than being left behind? Why did the stars show no obvious shift in position as Earth moves from one side of its orbit to the other? These were fair questions. At the time, the available evidence was genuinely incomplete. Stellar distances were vastly underestimated. The motion of distant stars due to Earth's orbit, what astronomers call parallax, would only be measured centuries later, because stars are so much farther away than anyone then imagined. So Copernicus did not deliver a finished truth. He delivered a better scaffold, a reframing that made more sense of the available evidence, even if it couldn't yet answer every objection. First models that move in the right direction are often imperfect. What matters is that they shift the problem. There's something worth appreciating in how Copernicus worked. He did not make speeches. He reasoned carefully, wrote meticulously, and trusted mathematics enough to let it challenge intuition. That can be harder than drama. Intuition says the sun moves. Mathematics says perhaps Earth does. Intuition says stillness is real. Reason says sensation can mislead. And perhaps the deepest lesson in this moment of history: when evidence removes a cherished center, we often look for a larger one nearby. If not Earth, then perhaps the sun. The instinct relocates rather than retires. That pattern would repeat. Galileo looks up. What Copernicus offered was a rearrangement of logic. What was still needed was a rearrangement of sight. Then came a device modest in size and enormous in consequence: the telescope. Galileo Galilei didn't invent it. Versions of the instrument had appeared in the Netherlands in the early 1600s, primarily as tools for watching distant ships. Galileo heard of the design, built improved versions himself with better magnification, and then did something that seems obvious only because history has already happened. He pointed it upward. When he turned the telescope toward the moon, he didn't see the perfect, smooth sphere that philosophical tradition had imagined. He saw mountains, valleys, rough terrain casting shadows at the edges of sunlight. The moon looked less like a divine lamp suspended in a perfect celestial sphere, and more like a place, irregular, textured, almost geological. This mattered deeply. For centuries, many thinkers had divided reality into two distinct zones: the imperfect earth below, where things change and decay and behave inconveniently, and the perfect heavens above, where celestial bodies move in flawless harmony. But the moon had craters. If the moon had rugged landscapes, then the heavens were made of the same imperfect material as everything else. Sky and earth might belong to the same physical universe after all. One wall had cracked. Then Galileo looked at Jupiter, and the crack became something larger. Beside the giant planet, he observed tiny points of light that changed position from night to night, sometimes on one side, sometimes on the other. Sometimes one was hidden behind Jupiter altogether. These were moons. 4 large ones we now know as Io, Europa, Ganymede, and Callisto. But their scientific meaning was even larger than their beauty. Not everything in the cosmos orbits Earth. That single fact weakened geocentrism more than any philosophical argument could. If small worlds circle Jupiter, then Earth is not the mandatory center of all motion. The heavens can host multiple centers of orbit. Nature had just demonstrated flexibility where doctrine preferred singularity. Galileo also observed Venus over many months and found something decisive. Venus shows phases: crescent, half-lit, nearly full, cycling through shapes much like the Moon. In the old Earth-centered model, Venus circling between Earth and the Sun could only ever appear as a thin crescent. It could never appear nearly full. But in the heliocentric arrangement, where Venus orbits the Sun inside Earth's orbit, the full range of phases follows naturally from geometry. Venus was, quietly and measurably, siding with Copernicus. Then Galileo turned the telescope toward the Milky Way. What had always appeared as a pale, cloudy band dissolved under magnification into countless individual stars packed so densely that human eyes had blended them into a glow. The universe was larger than it appeared. This pattern would repeat many times in the history of astronomy. Improve the instrument, enlarge the world. Now, it is tempting to tell Galileo's story as a clean contest between courageous science and stubborn ignorance. History is rarely that tidy. Many scholars engaged seriously with the new evidence. Some religious thinkers supported astronomical inquiry. Scientists disagreed among themselves for technical reasons. What is true is that Galileo argued forcefully and publicly, and with a sharpness that did not always improve diplomatic outcomes. He was brilliant, witty, and not especially committed to making enemies slowly. Eventually, this led to conflict with church authorities, trial, and house arrest. But the telescopic evidence could not be unseen. Once mountains appeared on the Moon, perfection was complicated. Once moons appeared around Jupiter, exclusivity was broken. Once the phases of Venus were observed, heliocentric geometry gained direct support. Once the Milky Way dissolved into stars, the scale of the cosmos expanded. The telescope didn't merely add facts, it altered the kind of universe people inhabited. Before it, the heavens were largely a visual dome. After it, the heavens became a landscape, layered in depth, populated, physical. A flat ceiling had become an ocean, and there is a gentle philosophical lesson somewhere in all this. Galileo didn't move mountains physically, but by seeing mountains on the Moon, he helped move minds on Earth. Sometimes, perspective changes through literal perspective. Use a telescope and certainty becomes negotiable. The world contains more than the census first report. Earth had now been removed from the center. The Sun held its place, for now. But something larger was quietly waiting, and it had to do with that pale river of light crossing the night sky. The Milky Way and our misplaced address. After Copernicus and Galileo, the Sun took on a new kind of dignity. No longer a lamp circling Earth, it became the gravitational anchor of the solar system. Planets traveled around it. seasons, daylight, and orbital order all tied themselves to this one glowing star. It felt natural to wonder whether the Sun might now occupy a larger cosmic importance. Perhaps we hadn't lost the center after all. Perhaps we'd simply been looking at the wrong object. This is a very human move. When one certainty dissolves, we relocate confidence rather than surrender it. Meanwhile, above on clear nights, that pale river of light, the Milky Way, stretched from horizon to horizon. Without modern light pollution, it would have been a luminous, textured presence, brighter in some regions, thinner in others. Ancient cultures imagined it as spilled milk, a road of souls, a pathway of birds. What it physically was remained an open question. Galileo's telescope had already hinted at the answer by showing the Milky Way was made of stars, enormous numbers of them, packed so densely that eyes blended them into glow. But how were those stars arranged? Were we at their center, near their edge, somewhere in between? In the late 1700s, the astronomer William Herschel attempted to answer this directly. His method was elegant for its time. Count stars in many different directions across the sky. If more stars appeared in one direction, the stellar system probably extended further that way. Fewer stars might indicate a nearby edge. After enormous effort, Herschel concluded that the Milky Way was a flattened, lens-shaped system, and that the Sun sat near its center. And there it was again, another center, another comfortable middle. Herschel wasn't being vain. He was reasoning carefully from available evidence. His assumptions seemed sound. That stars were distributed roughly evenly throughout the galaxy, and that his telescopes could see all the way to its edges. Both assumptions turned out to be incomplete. The problem was dust. Interstellar dust, vast clouds of gas and dark particles threading through the Milky Way, blocks visible light, especially along the dense plane of the galaxy. In many directions, Herschel's telescopes weren't measuring the edge of the galaxy at all. They were measuring how far light could travel before the dust intervened. The stellar system seemed to end roughly equally in all directions, not because we were central, but because visibility was equally limited in every direction. It was a false symmetry produced by incomplete access. The mind is vulnerable to this kind of error in many settings. Stand in fog and the world may appear equally bounded around you. That doesn't mean you stand at the center of the landscape. It means visibility has limits. For a long time, humanity lived inside a fog of stars and dust, and mistook the boundaries of sight for the boundaries of the galaxy. The correction came in the early 20th century through the work of an American astronomer named Harlow Shapley. His approach was different. Instead of counting stars, he studied globular clusters, dense spherical swarms of hundreds of thousands of ancient stars that orbit the Milky Way like luminous satellites. If he could map where these clusters were distributed in space, their arrangement might reveal where the main mass of the galaxy actually lay. To do this, he needed distances, and for distances, he used variable stars, stars that brighten and dim in regular cycles. Their pulsation periods are linked to their true luminosity. Measure how bright they appear from Earth, compare that to how bright they truly are, and geometry yields distance. The stars were, in effect, blinking coordinates. Shapley measured distances to many globular clusters and plotted their positions. What he found was striking. The clusters were not arranged symmetrically around the Sun. They were concentrated in the direction of the constellation Sagittarius, meaning the true center of the Milky Way lay far away in that direction. The Sun was not central at all. We were displaced, living tens of thousands of light years from the galactic core, in a quieter outer region of a spiral arm. Humanity had once again mistaken a local vantage point for a privileged position. Think of what this meant. Imagine growing up believing your house stands in the middle of a continent, then discovering you live in a distant suburb near one edge of a massive nation. The roads still function. Your home still matters to you. But the map feels entirely different. And perhaps there is something quietly reassuring in where we ended up. The galactic center is a dense, energetic, radiation-bathed environment, not especially hospitable to stable planetary conditions. Our suburban spiral arm location, far from all that intensity, may be precisely why the conditions for life were possible here. Sometimes not being central is an advantage. Anyone who has ever tried to sleep in the noisiest part of a city may find this relatable. Shapley didn't diminish us. He clarified us. He showed that our Sun circles in the outer districts of a galaxy so large it strains imagination, and that living far from the middle doesn't prevent life, thought, or meaning from arising. Position and significance are not the same category. But the instinct for a center simply scaled upward. If not our location within the galaxy, perhaps the galaxy itself was the center of everything. That idea, too, was about to be tested. The universe of galaxies. There is a particular kind of shock that science delivers, not through contradiction, but through multiplication. You think there is one mountain range. Morning fog lifts and reveals 10 more behind it. By the early 20th century, through the sky were scattered faint, cloudy objects called spiral nebulae, elegant whirls of light like tiny cosmic pinwheels. Were these nearby objects inside our galaxy, perhaps star-forming clouds? Or were they something else entirely? Vast stellar systems far beyond the Milky Way. This question was not minor bookkeeping. It was about the scale of reality itself. In 1920, the debate became explicit. A formal exchange between Harlow Shapley and Heber Curtis. Shapley argued that the Milky Way was enormous and contained the spiral nebulae within it. Curtis argued that at least some spirals were independent island universes, separate galaxies outside our own. Both men had pieces of truth, but neither could yet see the full picture. Enter Edwin Hubble. Hubble had an unusual path to astronomy. He studied law, boxed competitively, taught school. He eventually came to work at Mount Wilson Observatory in California, home to the most powerful telescope in the world at the time. With it, he focused on the Andromeda Nebula, a faint smudge visible to the naked eye on dark nights. He identified variable stars within it, the same kind of pulsating stars Shapley had used to measure distances. By comparing their apparent brightness to their known true luminosity, he calculated how far away Andromeda actually was. It was vastly, unreachably far outside the Milky Way. The Andromeda Nebula became the Andromeda Galaxy, an immense stellar system in its own right, comparable in scale to our own. The Milky Way was not the universe. It was one galaxy among others. Try to hold that for a moment. People had only recently adjusted to not being at the center of their own galaxy. Now they learned that the galaxy itself was not the whole stage, but one city among countless cities spread across a dark continent. As more observations accumulated, other spiral nebulae also resolved into galaxies. The sky was not sprinkled with a few local curiosities. It was crowded with island universes. Today, we use the word galaxy so casually that its strangeness can slip past unnoticed. A galaxy is not a star. It is a gravitational city of stars, hundreds of billions of them in many cases, along with gas, dust, dark matter, planets, and billions of years of history. And there are hundreds of billions of these cities in the observable universe alone. Then Hubble went further. He and others studied the light from these galaxies carefully, specifically its spectrum, the rainbow of wavelengths that reveals what elements are present. Many galaxies showed redshifts. Their spectral lines were displaced toward longer, redder wavelengths. Interpreted through the physics of motion, this meant galaxies were generally moving away, and crucially, the farther away a galaxy was, the faster it appeared to recede. The universe was expanding. Not galaxies flying through empty space from some central explosion. The space between galaxies was growing. Distances were increasing because the fabric of space itself was stretching. This is a strange sentence by ordinary standards, and we'll unpack it further. For now, the essential shift was clear. The cosmos wasn't static. It was evolving. And if everything is moving apart, the question of where the center might be becomes suddenly far more complicated. The Milky Way had been one candidate for the center of everything. Now there were hundreds of billions of candidates, and none of them obviously special. The throne room didn't merely empty, it multiplied into neighborhoods beyond counting, expanding space and the raisin-bread universe. If everything is moving apart, what is it moving away from? It sounds sensible. If you see fragments scattering outward, you assume there was a point of origin. Fireworks burst from a center, ripples spread from a splash. So when galaxies appear to be receding in every direction, many people naturally picture a cosmic explosion from one place. Matter racing outward into empty space, a center left behind somewhere in the distance. That picture is understandable. It is also, in important ways, misleading. The universe is not, as far as current evidence suggests, debris flying outward through pre-existing emptiness from a central blast point. The large-scale expansion is better understood as space itself stretching, and that distinction changes everything about where a center might be. The most famous illustration of this is raisin bread. Imagine a lump of dough filled with raisins placed in a warm oven. As the dough rises, every raisin moves farther from every other raisin. Not because the raisins are crawling across the dough, not because one raisin is pushing the others away. The dough between them expands. From the perspective of any one raisin, all the others recede. A raisin nearby drifts away slowly. A raisin farther off separates faster because more dough lies between them. No raisin is the special center of expansion. No raisin can point to another and say, "You are fleeing from me." The separation is mutual and geometric, a property of the dough, not of any one location. Galaxies are like raisins. Space is like the dough. On large scales, galaxies are not racing through space because of some explosion pushing them outward. Space between distant galaxies increases, so separations grow over time. And every galaxy, wherever it happens to be, sees others generally receding in this same broad pattern.
Not because it occupies the center, but because expansion belongs to the geometry of space itself. This has an elegant consequence. Every observer can appear to be at the middle of the recession pattern without any of them actually being cosmically privileged. Each sees the same law locally. The universe is, in this sense, democratic. There is another image that helps. Imagine an infinitely long road with towns equally spaced along it. If the space between every neighboring town doubles over time, then a traveler in any town sees all other towns receding, and distant towns receding faster. Every traveler sees the same pattern centered on themselves. The rule is universal, not personal. Observation point is not command center. This is one of the deepest shifts in how we think about cosmic expansion. We often confuse measured from here with caused by here. Some listeners may wonder, if we run time backward, doesn't everything converge on one single point? Only if we imagine matter compressing through ordinary pre-existing space toward one location. In the standard cosmological model, running the clock backward means the scale of space itself was smaller. Distances were compressed generally, everywhere. The early universe wasn't matter piled into one corner of a vast, empty room. It was a hot, dense state of space itself, spread throughout what would become the observable universe. The Big Bang was not an explosion in space. It was an early state of space. That sentence takes a moment to settle, and that's appropriate. Some truths are not difficult because they're impossible to grasp. They're difficult because they refuse to resemble anything in ordinary life. We evolved to navigate kitchens and weather and social situations. We were not built to picture dynamic space-time. Be kind to the brain as it stretches. There is one last thing worth savoring about raisin bread. Bound systems don't participate in expansion. Gravity holds atoms, planets, stars, and galaxies together. The Milky Way and Andromeda are actually moving toward each other and will eventually merge. Your furniture is not drifting apart due to dark energy. Expansion dominates only on scales large enough that gravity cannot overcome it. So your socks are disappearing for entirely different reasons. The shape of everything. Take a coin and set it on a table. It has an obvious shape, a clear boundary, a center you can point to. This is how intuition approaches the universe, as a very large thing with a form, and therefore a middle. But the universe may not be a thing in that sense. It may be the total extent of spatial relations themselves. And that makes the question of shape subtler
and more interesting than it first appears. When cosmologists ask about the shape of the universe, they don't mean whether it resembles a cube or a sphere sitting in some larger room. They mean something more fundamental. What is the geometry of space on the largest scales? Is it flat? Positively curved? Negatively curved? Finite or infinite? Does it wrap around itself so that traveling far enough in one direction might bring you back to where you started? These are genuinely different questions from simply asking where the middle is. And crucially, none of them necessarily produce a center. Consider Earth's surface as an analogy. If you live on the surface and can only move across it, no jumping off into space, your world has area and shape. It is curved. It is finite. Yet it has no edge to fall off, and no uniquely privileged point on the surface that serves as the center of all travel. You can walk north, south, east, west, cross oceans, traverse continents, and never step onto a tile marked center. Every city can call itself central in its own tourist brochure. The surface itself is unimpressed. Our three-dimensional universe may work similarly. It may possess global geometry without containing a center within the space that we actually inhabit. The three main geometric possibilities scientists discuss are these. First, flat space, where parallel lines stay parallel, triangles behave as familiar geometry predicts, and space may extend infinitely without end. In infinite flat space, asking for the center becomes almost meaningless. Every point can claim to be surrounded by more space in all directions. Infinite uniform space has no obvious middle. Second, positively curved space, loosely analogous to a three-dimensional version of a sphere's surface. Travel far enough in a straight line, and you could theoretically return to your starting point. Finite, no edge, no center in the lived sense. Third, negatively curved space, where triangles have angle sums less than 180 degrees, and the geometry opens outward rather than closing. Also strange, also not obviously providing a throne room. How do we actually measure this? With ancient light. The cosmic microwave background, which we'll visit shortly, combined with large-scale surveys of galaxies, allow scientists to estimate the curvature of the observable universe. Current evidence suggests space is very close to flat on large scales, within measurement precision. Very close to flat doesn't necessarily mean infinite, but it means if curvature exists, it is subtle enough that our observable region looks nearly flat, like standing in a vast plain where Earth's curvature isn't obvious from ground level. There is also an important distinction between the observable universe and the entire universe. We can only see out to the distance light has had time to travel since the early universe became transparent. A horizon, not a wall. Beyond it may lie vastly more space, perhaps infinite. We don't yet fully know. So even if we placed ourselves at the center of our own observable sphere, which in a trivial sense we do since we observe from here, that doesn't make us the center of all that exists. Every observer has an observable sphere centered on themselves. Many local horizons. No single universal center required. Here again, perspective masquerades as privilege. A universe without a geometric center might feel impersonal at first. But consider what it actually implies. No region owns reality more than another. No galaxy holds an official title. Laws apply broadly. Stars form in many neighborhoods without waiting for permission from a central authority. That is a generous and oddly egalitarian cosmos.
The oldest light. Long before galaxies formed their elegant spirals, before stars ignited in great numbers, before any planet cooled, the universe was bright everywhere. Not bright in the gentle sense of morning sunlight, bright in the way an extremely hot, dense, and opaque early cosmos would be. Matter and radiation were so tightly packed and so energetic that light couldn't travel freely. Photons scattered constantly, trapped in a glowing fog. The young universe was less a clear sky and more a luminous soup. Then, roughly 380,000 years after the Big Bang, temperatures dropped enough for electrons and atomic nuclei to combine into neutral atoms. Suddenly, light scattered far less. Photons were able to stream outward through space for the first time. The fog cleared. Those ancient photons are still traveling today, stretched by billions of years of cosmic expansion into microwave wavelengths. They fill the universe in every direction as a faint relic glow known as the cosmic microwave background, the CMB. It was discovered almost by accident in 1965. Two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubled by a persistent background noise in their microwave antenna that they could not explain. They checked their equipment. They checked for interference. They cleaned pigeon droppings from the antenna dish, making them perhaps the only Nobel-linked scientists whose path to discovery included that particular maintenance task. The signal remained, coming equally from every direction in the sky. They had found the afterglow of the early universe. Pause with that sentence. Human beings on one small planet detected radiation left over from when the cosmos was less than 500,000 years old. We noticed it as static while trying to clean a radio dish. Science can be wonderfully undramatic. Why does this matter for the question of a center? Because the CMB is extraordinarily uniform across the sky. Measure its temperature in one direction, then another, and you find nearly the same value everywhere. About 2.725 degrees above absolute zero. The variations that exist are tiny, only about 1 part in 100,000. That smoothness is one of the strongest pieces of evidence we have that the universe has no privileged center. If there were a grand central region around which everything else was arranged, a cosmic hotspot, a preferred location, we would expect to see it reflected in the relic radiation. We would expect clear directional signatures, obvious asymmetries, one warm side and one cool side. Instead, ancient light arrives from all directions with remarkable consistency. The early observable universe was nearly even in density and temperature, with only slight fluctuations. Those fluctuations matter enormously. They are the seeds from which gravity eventually built galaxies and galaxy clusters, including everything we can see today. Without them, matter would have spread perfectly smooth, and nothing interesting would ever have formed. Tiny unevenness gave rise to everything. including, eventually, someone listening to this in a quiet room. There is one asymmetry we do observe in the CMB, a very slight pattern caused by our own motion through space. The Milky Way, the local group of galaxies, and Earth itself are all moving relative to the frame in which the CMB appears most uniform. Because of this motion, the background radiation appears slightly warmer in the direction we're moving toward, and slightly cooler behind us. A Doppler effect, like the changing pitch of a passing train. This doesn't reveal a center of the universe. It reveals our velocity relative to the ancient light field. Subtract that motion, and the background becomes strikingly even. Again, perspective can look like privilege. They are not the same thing. The CMB also carries another lesson worth carrying into sleep. The darkness above us is not empty. Right now, in every direction, ancient microwave photons pass through the room, through the walls, through everything, traveling since before any star that you can see tonight had ignited. The darkness is full of memory. We didn't know this until we built the right instruments. Reality exceeds unaided perception by a generous margin, and that will likely remain true no matter how sophisticated our instruments become. Every observer at the center stand at any window in any city in the world and look out. Streets and buildings arrange themselves around your perspective. The world spreads outward from where you stand, not because you are the sovereign ruler of geography, but because perspective always organizes experience around the observer. This simple fact, so ordinary we barely notice it, becomes strangely important when applied to cosmology. When astronomers look at distant galaxies, they observe that on average, galaxies are moving away in every direction. This recession pattern doesn't single out one central galaxy. It appears from many different locations. Wherever you are, distant galaxies tend to recede. And this might seem to imply that every galaxy sees itself at the center of the universe simultaneously, which sounds impossible until you understand what kind of expansion is actually happening. Imagine an infinitely large, stretchy sheet covered with dots, all equally spaced. If the sheet expands uniformly, every dot moves farther from every other dot. If you are dot A, all other dots move away from you. If you are dot B, the same is true. If you are dot C, the same again. No contradiction occurs because expansion belongs to the sheet, not to any one chosen dot. Likewise, in cosmology, recession belongs to the geometry of spacetime on large scales. Every observer describes the same law locally. This is captured in what cosmologists call the cosmological principle. On sufficiently large scales, the universe is roughly similar from place to place, and roughly similar in all directions. Not perfectly. Nearby reality is gloriously lumpy, full of galaxies and clusters and great empty voids. But average over vast enough scales, and no preferred place or direction strongly dominates. This is why every galaxy can appear central in the expansion pattern without any of them actually occupying a unique middle. There is no throne. There is a rule that applies everywhere equally.
Another way to feel this: suppose towns are spaced along an infinite road, and the distance between every neighboring town doubles over time. A traveler in any town sees all other towns receding, with distant ones receding faster. Every traveler sees exactly the same pattern, seemingly centered on themselves. The rule is universal, not personal. Human psychology often confuses measured from here with caused by here. Traffic seems arranged against your schedule. Weather seems to happen specifically to your plans. And cosmic expansion can seem centered on us, because we observe from us. But observation point is not command center. Some people, on hearing all this, feel a different kind of loss. Not just the loss of a cosmic middle, but a subtler loss of significance. If no place is special, does any place matter? This is where the question reveals itself as more psychological than astronomical.
Meaning and centrality are not the same category. They have been culturally linked for so long that separating them can feel strange. But consider, a melody doesn't need a central note to move you. A forest doesn't need a chief tree to be beautiful. A friendship's value is not stored in its coordinates on a map. Significance emerges through relationships, consciousness, care, experience, and attention, none of which require a cosmic address. In fact, a universe with no preferred middle may hold a deeper kind of fairness. No region owns reality more than any other. No civilization, if others exist somewhere out there, would occupy the ordained capital of creation. Laws apply broadly. Stars form in many neighborhoods. Possibility is distributed generously. You are not at the center of the universe. You are, right now, at the center of your conscious experience. Sounds arrive from where you are. Breath happens in your body. Memory and anticipation meet in this moment. That kind of center is intimate and immediate and genuine. It doesn't compete with cosmology because it belongs to a different category entirely. Physics describes structure. Experience describes being. Both matter. So, is there a center of the universe? Probably not in the way the question imagines. Not a cosmic downtown. Not a marked point from which all distances make sense, where space itself nods and says, "This is the spot." Every time that idea seemed within reach, the frame expanded and quietly escorted us elsewhere. Earth was not the center. The sun was not the center. Our place in the galaxy was not the center. Our galaxy was not the whole universe. Expansion has no single launch point. Space has no obvious middle. Ancient light arrives from every direction with remarkable evenness. And yet nothing was actually lost in all that wandering. Not wonder, not meaning, not the capacity to ask good questions in the dark. The universe appears to be the kind of place where significance is not issued from headquarters. It arises locally, in stable stars, in orbiting planets, in oceans and chemistry, in the slow, patient emergence of minds able to notice that they exist and wonder what kind of thing they exist inside. You are not central to the cosmos. You are part of the cosmos. That is not a smaller thing. Matter became curious about matter. Hydrogen, given enough time and complexity, learned to ask where the middle is. Tonight, let that be enough. Wherever you are, small room or open window, city hum or countryside stillness, the ancient microwave glow of the early universe passes through the walls right now in every direction. The oldest light there is, traveling since before any star you can see tonight had ignited. It has no center. It has no edge. It simply continues. And somewhere within it, you are here, briefly, wondering. Thank you for spending this time on Science for Sleep. If this journey brought you a little calm or a gentler ending to the day, feel free to return whenever you'd like another slow walk through a difficult question made softer. For now, let the room be quiet. Let this moment be enough. Let yourself rest.